Alright guys, I had to do this video in two parts because I had a little editing issue. So we are going to go through an example problem of if I have a solution that is aqueous. So the solution I want to use for this example is copper 2 sulfate, so CuSO4. And remember, the little aqueous thing means that water is present in here, so we have to kind of figure out, is the species going to be reduced or is water reduced instead? Is the other species going to be reduced or is water going to be reduced instead? So let's go through this and talk it through. And so I look at my cation and my anion. So in this solution, Cu is going to be my cation because Cu gets the positive, remember positive for your cations, positive 2 charge. Your sulfate is going to be your anion because it is a negative 2 charge and anions are negatively charged. And so we have to evaluate this further and figure out the rules that are involved. So the rule says, looking at copper, if your cation is a group 1 or 2, water will be reduced instead. So copper is not a group 1 or group 2. So what does that mean? That means that copper will actually be the species reduced. And so let's write our half reaction there. So we have Cu 2+, remember if it's reduced, it starts out as its ion, plus 2 electrons transferred, which yields Cu. And so that is going to be the reduced half reaction. And remember, reduction occurs at our cathode. So we will have that labeled as our cathode when we go back up here to labeling. Before we do that, let's talk about the species that will be oxidized. Now, for the oxidized rule, it says if the anion is a polyatomic ion, water will be oxidized instead. So we do have a polyatomic ion that is present here. And so what does that mean? Because this is a polyatomic ion, this sulfate is not going to be oxidized. It's just going to remain floating in the solution here. Instead, water will be oxidized. And so when we write the half reaction, we have to write the half reaction for water going to oxygen because that is the oxidized half reaction. So I'm going to rewrite this. 2H2O yields O2 plus 4H plus 4 electrons. And so yes, you do have to write out that whole entire species. That is the complete half reaction. And so this is what is occurring on our oxidized side, which is our anode. So let's take these half reactions and label our electrolytic cell. So I'm just going to say that copper, I'm going to use my red again. Copper is going to be my cathode, right? And so let's just put our copper on this side. I'm just choosing where I want it to be. And so that will be our cathode. It is our cathode because that is where reduction occurs. What will be our anode? Now, normally we would say, okay, well, O2 is the species that it's oxidized. That will be our anode. But because oxygen is a gas, we cannot use it as our electrode. Instead, we have to use one of these inert electrodes. So you can use platinum or you can use graphite. You don't have to use both, one or the other. So I'm just going to use platinum for this particular one. It's an inert electrode. And what we will see here, because oxygen is a gas, is little bubbles that are forming. And those bubbles are going to be our oxygen gas that is present. So this will be what is happening at the anode, because anode is where oxidation occurs. Now, what will be in our solution? Our solution will have copper 2 pluses and sulfates floating around in there. And remember that that is your aqueous solution. So there's little water molecules that are present in here as well, and that's why we're able to get this oxygen gas produced on this side. We will not be forming hydrogen gas, however, because your copper will be the species that is reduced instead of the water forming hydrogen gas. And so this is how we can figure out and label our things in our electrolytic cell if we're dealing with aqueous solutions. Now, the question that I want to leave you with at the end is, how do these electrons travel? Well, they're still going to travel anode to cathode. So we're going to go from the anode to the cathode. One extra thing that I kind of want to talk to you guys about is being able to write these total net ionic equations for the species that have water involved in it. Some students have a difficult time being able to write those equations. And so I want to show you guys how I would write the total net ionic equation for this one. So I'm going to take a second and erase this just so I can have more space. All right. So I want to rewrite these half reactions up here. So we have Cu2 plus 2 electrons yields Cu. And we also have 2H2O yields O2 plus 4H plus 4 electrons. Now, my goal is to write the net ionic equation for what is happening here. When I write my net ionic equation, what I have to do first is balance my electrons on both sides. So we have a yield sign right here, and we have a yield sign right here. Do you see how there's 2 electrons on this side and 4 electrons on the opposite side? I never have electrons in my total net ionic equation, right? Because electrons are only presented in the half reactions. So in order to cancel these out, I have to have the same amount on opposite sides of the yield sign. Well, how can I get there? Well, what I'm going to do is I'm going to balance these electrons. And remember, from galvanic cells, this is how we get our N value, our total moles of electrons transferred. And so 4 would be our total moles of electrons transferred in this reaction, because I would want to multiply this whole entire reaction by 2. If I multiply that entire reaction by 2, this 2 distributes, so I now have 2 Cu2 pluses, not 2 but 4 electrons, and 2 Cus that are present here. I now have balanced my electrons on opposite sides, and they are able to cancel out. Once I complete that, I just bring everything else down. So I have 2 Cu2 plus 2 H2O. Do you see how I've written that and written that? These are all the things that are on the left-hand side of my yield sign. On the right-hand side of my yield sign, I have O2 plus 4H plus. So that's O2, 4H plus, and 2 Cus. This right here, guys, would be my total net ionic equation for this electrolytic cell. And so all we have to do is balance our electrons and then put everything together on the left-hand and right-hand side of the equation line, or the yield sign, sorry. So that's how we do electrolytic cells if we have an aqueous solution. We're going to go through some example problems and talk about the math with the electrolytic cell as well. Hope this was helpful.